Intermediate Algebra, Section 3.2, solving a system of linear equations with two unknowns by using the substitution method. Algebraic, non-graphical methods for solving systems are often superior to graphing, especially when fractions are involved. One algebraic method, the substitution method, relies on having a variable isolated. So we move from graphically to substitution. As another method for finding our solution. So let's take a look at this first example. They're asking us to solve the system using the substitution method. And just for reference, I'm going to number these equations. For the substitution method to work, we have to have one of the equations with a variable isolated. And as it turns out, that is the case here. We have y by itself. We have two unknowns, so we do need the two equations. And to solve this using substitution, I'm going to rewrite this first equation, 3x plus, and I'll identify it with the equation 1, 3x plus, but instead of y, since we have y here isolated, I'm going to replace that y with what it's equal to from the second equation. So here's the y, only the equivalent, 2x minus 5 is equal to 5. So this is my first equation, 3x plus y is equal to 5. What that's done has swapped out one equation with two variables, which is not possible to solve, to one equation with one variable, which we can go ahead and solve. Underlining was just simply for illustration purposes, so I'm going to go forward and solve this equation by combining like terms. 3x plus 2x is 5x, minus 5 is equal to 5. Isolating the variable, we'll add a 5 to both sides. That leaves a 5x equal to 10, and then divide both sides by 5 so that x is equal to 2. So these two linear equations do intersect. They have a common point with an x-coordinate of 2. What will the y-coordinate be? We can replace x in either one of the two equations. To solve for y, it's probably easier here in the second equation since y is already isolated. The x value that we found that's common is 2, so I'm replacing x with 2. Multiplying to simplify, we have 4 minus 5, or 4 plus a negative 5 leaves a negative 1. So if we graph these two equations, which graph into lines, we would find that they have a common point of intersection at 2, negative 1. Here we have another example asking us to solve the system using the substitution method. And again, we need to have one variable isolated in an equation, then we're ready to substitute, and this is already set up. And just for reference, I'm going to number these two equations. So we have y is equal to negative 3x plus 4, and here in this second equation, we have the x and y. One equation with two unknowns we can't solve, but because we have this second equation, and we're going to use the substitution method, I'm going to replace in this second equation the value of y, which from the first equation is indicated as negative 3x plus 4, and then continue writing the rest of equation number 2. So I have 6x plus 2 times y, but y is negative 3x plus 4 from the first equation, and then the rest of 2, minus 12 is equal to 0. By swapping out the y with an equivalent value or expression in terms of x, I now have one equation with one variable. I can now simplify this, and to start out with, we need to do a distributive. 2 times negative 3x is a negative 6x. 2 times 4 is 8, with the minus 12 is equal to 0. Simplifying further by combining like terms, the x terms are additive inverses and they cancel out, leaving us with 8 minus 12, or 8 plus a negative 12 is a negative 4, is equal to 0. What we have is a contradiction. And furthermore, it's false. Negative 4 does not equal 0. Whoops, false. What that means is that we have no solution. And if we graphed these two lines, we would find that they graph into parallel lines with no intersection. So to answer this, we would say no solution, and to help understand that, we would find that they are in fact parallel lines. In this last example, same thing again. They're asking us to solve the system using substitution method. If we had the equations where one variable was not having a isolated like this, we would have to do that as our preliminary step, but we're fortunate here again that they're just set up, ready to go for substitution. I've numbered the equations. I'm going to use the fact that x is equal to 4y plus 3 to swap out x in the second equation. So here's the new version of the second equation. 2 times x, but since x is equal to 4y plus 3, I'm replacing it, and then I write the rest of the second equation. So it's 2 times x, and the value we got from x is from the first equation, minus 8y equals 6. We now have one equation with one variable that allows us to go forward and solve. First, though, we need to use our distributive method. 2 times 4y is 8y, 2 times 3 is 6, minus 8y is equal to 6. Simplifying, when we combine our like terms, the variables are canceling out here as well. They're additive inverses. 8y minus 8y leaves no y, but we have the 6 equal to 6. This is an identity. When the variable is gone, we have two possibilities, like the last one, where we had a contradiction and no solution because the equations were actually parallel. Here, we have an identity, it's true, and we have a system of infinite solutions, which means if we graph these, we would find that we have the same line, and anything that satisfies one equation is going to satisfy the other. So our solution is infinite, and for notation purposes wise, we could say the points are xy such that x is equal to 4y plus 3, writing one of the equations for our rule for this system of equations.